Welcome to the content material for Class 22 of Engineering Statics. You should be watching this video before your 22nd class. In today's lesson, we will learn the theory of dry friction and how to solve problems involving friction. Today, we are talking about dry friction. There are other types of friction, such as fluid friction or internal friction, but we will not talk about those in this course. Dry friction occurs between two surfaces in contact with one another. The friction force always acts in a direction opposite of the relative motion of the two surfaces. So imagine we have this box sitting on a rough surface. The box has a weight W, and there is also a normal force N pushing back up on the box. That force N is actually a distributed load, but we can simplify it to an equivalent concentrated force. If we start to apply a force P to pull the box, some things will change. First, the distributed load will change. As the force P pulls the box, it will try to rotate, so more force will be on the right side, meaning the corresponding normal distributed force shifts to the right. The second thing that changes is that the friction force will oppose the pulling force. In equilibrium, which is what we assume in this class, the forces P and F are equal. But you can imagine that if you keep pulling harder and harder, at some point the pulling force will overcome the friction and the book will begin to slide. But when does this happen? The phenomenon of friction can be described by Coulomb's theory of friction. Let's imagine a book sitting on a table. And the book has a weight W, and there is a normal force pushing back on the book, N. Then let's imagine we start pushing on the book with a force P. We start with a tiny push and slowly increase the force. At first, the book will not move. The friction force resists the pushing, and the friction force F is equal to the force P. This is the first phase of Coulomb's friction, in which the book does not move. We call this phase static and no impending motion, or simply no motion. In this situation, the force F is equal to the pushing force P. In this phase, we can increase the force P, and the friction force equals it without any motion. At some point, however, as we increase the pushing force, we will reach the maximum force that friction can handle. This maximum is the second phase, which we call impending motion. The book still isn't moving, but if we increase the force just a little bit, it will start to slide. In this situation, the friction force is equal to the normal force times the static friction coefficient, or μs. The coefficient μs depends on the surface material. For example, metal on ice has a coefficient of only 0.03 to 0.05. Wood on wood, however, is very rough and has a higher coefficient of 0.3 to 0.7. Some materials even have a value greater than 1, but that is rare. At this point, if we increase the pushing force any more, the book begins to slide. Once in motion, the friction force actually decreases. In other words, if the object is moving, the object will slide more easily. This is phase 3, which we call in motion. At this point, the friction force is equal to the normal force times a new friction coefficient, which we call μk, and k is for kinetic. So how do we know which phase of friction we are dealing with in a problem? Well, we can use clues in the problem statement to recognize which situation the problem is describing. Phase 1, which is no motion, means that the friction force is equal to the pulling or pushing force. The key to recognizing this kind of problem is that it will say the object is sitting or static. For example, a force is applied to the box which is not moving. What is the friction force? In this type of problem, we solve for the friction force based on equilibrium and then check that the force is less than μs. In phase 2, which is impending motion, it means that the friction force is equal to the normal force times the static coefficient, μs. The key to recognizing this kind of problem is that it will ask about a maximum or a minimum. For example, what is the maximum force that can be applied, or what is the minimum coefficient of static friction? And in phase 3, which is in motion, it means that the friction force is equal to the normal force times the kinetic coefficient, μk. The key to recognizing this kind of problem is that it will say that the object is moving at a constant velocity. For example, what is the coefficient of friction to keep the velocity constant? So let's look at an example of a few of these. So in this example, we have a wooden crate. And we're told that the crate has a mass of 20 grams, so it has a weight. And we're told that there's a force P, which is at an angle of 30 degrees. And so we can go ahead and break that into its x and y components. And the force is 80 newtons. And the other thing we know is that the coefficient of static friction is 0.3. So we can draw our normal force. We know that there's a normal force pushing back up from the table. And what we're asked to figure out is whether or not this crate will remain in equilibrium as this force is applied to it. So if it's in equilibrium, that means that the forces in the x are equal, so we have px would be equal to our friction, which is pushing back. So the friction coefficient is going to go against the impending motion. So because the force is trying to push the crate to the right, the friction force will push back to the left. The other thing that we know is that if it's in equilibrium, we know in the y direction that W and Py, our two downward forces, would be equal to the one upward force, N. So we're going to solve for this situation and then check if that will remain based on the maximum amount of friction force that can occur. So we'll solve for the x. Find that Px is equal to 69.28 newtons. And so since the friction force is equal to that, we know that the friction force, therefore, would be equal to, under conditions of equilibrium. Conditions of equilibrium would constitute phase 1 of the Coulomb graph. So we're assuming in this case that the friction force is equal to P. Next we'll solve for the y. When we solve, we can find that the normal force in this case is equal to 236.2 newtons. Okay, now to know whether or not this stays in equilibrium, we have to check to make sure that that friction force is less than the maximum static friction that can occur, which would be phase 2. So we need to check that F is actually less than the normal force times the static friction coefficient. If it turns out that F is greater than that, it means that the force is enough to overcome the friction force and the box will start to slide. And therefore the crate is no longer in equilibrium. So we're going to check that this condition is met. So we'll solve. Okay, so we see that the friction force is in fact less than the normal force times the static friction coefficient. So the answer is yes. The crate will remain in equilibrium. In our second example, we see here there is a dump truck. In the back of the dump truck is a vending machine, and the dump truck is angled at 25 degrees. And what we're told is once that dump truck reaches the angle of 25 degrees, that vending machine is on the verge of sliding off. So with this information, we know what we're dealing with here is phase 2. It says it's on the verge of sliding, so that means that we can assume that F is equal to the normal force times the static coefficient. If the angle increases any more, the vending machine will start to slide as the forces are too strong for the friction coefficient, for the friction force. Okay, so how do we do that? Well, again, we know in this case that the friction force is going to be equal to the normal force times that static friction coefficient. And what we're asked to solve for is, what is that value? So, let's draw our diagram. So in my diagram, what we see is that first, this friction coefficient is pointing to the left. And that's because the impending motion, in other words, the motion that the fridge is trying to slide is to the right. So the friction force will be opposite to that. The second thing I'm going to do is I'm going to break up W into X and Y components. Actually, what I'm doing here is I'm rotating the X and Y axes by that 25 degrees. And that will just make my calculations a little bit simpler. So, if I do that, it means that Wx, well, what is that? We have to draw a little bit of a diagram here. So we know that this is 25 degrees. Therefore, this must be equal to 65 degrees, since that's 90 minus 25. And this must be also equal to 65 degrees. So if this is Wx and this is Wy, then that means that Wx is equal to W times the cosine of 65 degrees. Wy is equal to W times the sine of 65 degrees. And now I'll set up equations for equilibrium, starting with x. Using my rotated x-axis, I see that there is a friction force to the left, and Wx to the right. So our friction force, which we already know is equal to mu s times n, is equal to the x component of the weight. If we solve in the y direction, we see we only have the normal force and the y component of the weight. So the normal force is equal to Wy. So I can bring these two equations together. When I do that, I see that mu s times wy is equal wx. Solving for mu s, and what's nice here is that it's regardless of the weight, so we don't even have to know what the weight of the vending machine is. When we solve for mu s, we find that it is 0.466. So this is the static friction coefficient between the fridge and the dump truck, such that the vending machine would be on the verge of sliding down the truck at an angle of 25 degrees.